So I think when we were first giving examples of acyclic resolutions, I told you that the RAM sequence, the RAM complex, cohomological complex, is a cyclic resolution of the constant, the locally constant sheaf of, so the sheaf of locally constant functions. And I said the reason it was acyclic is because these are sheaves of C-infinity modules. So modules over the ring of smooth, over the sheaf of rings of smooth functions. And I didn't remember if we proved this fact or not. And we're actually going to prove it now. So at the time, the example was just an example without a proof, and now we finally get the proof. So today and tomorrow, we will just review applications of all this machinery. And we'll put together a few things we did in the semester. So yeah, so I was saying the first thing we're going to prove is that given a smooth manifold and a sheaf of infinity M modules, so a sheaf over the sheaf of rings, then this is acyclic. So acyclic, remember, means that the cohomology is 0 whenever P is greater than 0. And the proof is not too hard, and it's based on the existence of a partition of unity. So we start with a locally finite cover. Such that every open set is compactly contained in M. So this double inclusion means compactly contained, meaning that the closure is compact. And we take rho alpha be an associated partition unity. Okay, so now we take cochain. So an element, so just a P cochain such that it goes to 0. So an element of the kernel, which means a representative of an element in the cohomology. Yeah. And all we want to do is find the primitive. So find something in CP minus 1, which is mapped to this G. And this is not too hard because we can consider rho beta times G beta alpha 0 alpha P minus 1. So again, here we have P indexes, plus and the beta. So this is an element of U alpha 0 intersecting set to U alpha P minus 1. Okay, in principle, this is should be defined also on intersected beta, yeah, because this object here should be is not defined everywhere here. This G object is not defined everywhere here. You need to add intersected U beta, but the fact that we put this partition of unity here guarantees that this is well defined, because we just define it to be 0. But defining it as 0 outside the support of rho beta. Okay. And now if we want to get an element, sorry, this should have been a P minus 1. No, sorry, this is a P. Sorry, my bad. This is correct. Everything is correct. And now if we want to, now we kind of want to remove this beta from the equation. So we take F alpha 0 alpha P minus 1, just the sum over beta of these elements. You see, each of the sums takes place in this open set, u alpha 0 intersected u alpha p minus 1. So this is an element of cp minus 1 u f. And this is in fact the primitive, and that is an exercise. Verify that delta of this element is in fact this element. Just for practice, to convince you that this is true, let's just do it for p equal 1. So we take delta of f alpha 0. We look at it in position alpha 0 for 1. Then, by looking at this property here, this is f alpha 1 minus f alpha 0. Just by definition, yeah, of delta. And then we simply replace these two with the way we define them. So the sum in beta of rho beta, which appears in both instances. So just put it here, minus g beta alpha 0. So this is how we define our f alphas. And now we use the fact that the delta of g is 0. Because this means that this object together is simply g alpha 0 alpha 1. And since that's the partition of unity, this is g alpha 0 alpha 1. Okay, so now we know that every time we have a sheaf made of infinity m modules, then this is always a cyclic. So we know a few, of course, such modules. And one such module is, of course, the ring of smooth functions itself. So where did we see this ring of smooth functions? When one possibility is to stick it in the exponential sequence. So remember, we did the exponential sequel for the sheaf of holomorphic functions. But of course, we also said it could be, we could look at it for the sheaf of smooth functions. So if we take a manifold, then we take the exponential sequence in the smooth category. Gives the long exact sequence. HP m to infinity m, which we'll know will be 0. And then here you put non-zero maps. So this is the exponential map here. And then you go up by 1. And here you get 0 again. Okay, so this is a long exact sequence. And let's say for p greater or equal than 1, this term is 0 and this term is 0. So this gives us that HP m is infinity m star. It's isomorphic to HP plus 1 mz. And in particular, if we look at it for p equal 1, this gives that the h1 of m is infinity m star. It's isomorphic to h2 with integer coefficients. And why do I care so much about this p equal 1? Well, because remember, we looked at the h1m, and then here we put the holomorphic non-zero functions. This is precisely the Picard group of the manifold, if m is a complex manifold. No? So we can think of this with really the same proof as some sort of smooth Picard group. So this object here classifies all bundles of rank 1 up to isomorphism. So we think of it as a smooth Picard group. And of course, you can think of this as rank 1, real rank 1. So if the functions have values in R, but you can also think about it as functions with complex values. So rank 1 complex. So this is complex vector bundles. Okay, but not holomorphic vector bundles. So complex vector bundles just means that each fiber is a complex space, but the transition functions need not be holomorphic. Okay. And I mean, even to talk about holomorphicity, you need that M is a complex manifold, which we're not even asking here. So in particular, from this fact, we get that if this second cohomology group with integer coefficient is trivial, then every complex bundle of rank 1 on M is trivial. So looking again at this exponential sequence, so if M is, in the case of a complex manifold, so now we go back to holomorphic functions, we have a morphism denoted by C1, which goes from the Picard group into the second cohomology group with values in R, which is just, in fact, that map from the snake lemma plus some inclusions. Yeah, because you just think that C1 goes from the Picard group, but this is isomorphic to the H1M O star. And here we have the snake's lemma map, right? And this one we can just put it into H2MR. And sorry, here I put the inclusion thing, but it's not always an inclusion. So I should just put this. Of course, Z into R is an inclusion, but the induced map is not necessarily inclusion anymore. And this map is important, and we call it, I mean, the first, given a line bundle, so an element of the Picard group, we see that C1L, so this is an element here, is the first Chern class of L. And observe that all these were morphisms of groups. So in particular, if you take, so observation, if you take the first Chern class of a tensor product of line bundles, what you get is the sum of the Chern classes. So C1 is actually a morphism of groups. Okay, so now that we have this Chern class, it would be interesting to know what it looks like. Yeah, so let's say I give you a bundle and you can compute this Chern class, which is, of course, an invariant. Huh?
Yeah, just 1 second because I'm a little confused. Why isn't it 0? Is is that not an exact sequence that you're hovering over?
This one?
Yeah. This.
No, because remember, so the exact sequence, so the exponential sequence is 0, Z, holomorphic, non-zero, right? This is the exact sequence. So the long exact sequence that we'll get is like this, no? So I'm starting from here. So from here to here,
yeah,
is 0, but here I'm just putting something else.
Okay,
So
and the
this is
map
the
is
map induced from the inclusions into R.
okay. Good. Then I'm good.
This is induced from this.
Okay.
Okay. Okay, yeah, let's just do it in the next page. So we have this, yeah, given a bundle, this churn class, this first churn class gives you just a two form. Yeah. And it would be nice to know what does this two form looks like in terms of the bundle. So this is actually quite explicit. So we start with a complex manifold. And we take a cover. Such that, and we do need a special cover. So we need each intersection to be simply connected. For all JK such that this is not empty. So we take a line bundle on M with transition functions. G, J, K. Then the first chunk class is represented by an element with 3 indices in a suitable check cohomology group. So when I say represented here, of course, this first chunk class is an element of H2MR, right? But we know since that is the direct limit of this kind of objects, there is going to be some representative for some U, okay? So I'm saying that if you take the direct limit of this, the image on the direct limit, then you get precisely the C1L. Right. And what are this ZKJL? So this is I over 2 pi times the logarithm of JK restricted to UI intersected UK intersected UJ minus the log of JL UJ UK UL plus the logarithm of GKL restricted to UJ KUL, where log is any holomorphic logarithm. Any fixed holomorphic logarithm. And this exists because these are simply connected. Okay. So in each one is their own, yeah. So each of these log, it's like you take a log. So in UJK, so the intersection J intersected UK is simply connected. So you have a logarithm. You have many, you just take one. And you take this logarithm and then you restrict it. UJK, UJL, you have a logarithm, you take it, you restrict it. And the point that if you take a different logarithm, you know that two different logarithms are differ from each other by I2k, I2 pi k, right? So if you take a different logarithm, all you would get here is plus 2I pi k, which simply becomes minus k after this approach here. But then this represents the same class. So let's prove this fact. Maybe we'll need a new page. So as we were saying, since this intersection is simply connected, GJK admits a logarithm. Which, by the way, is unique up to 2 pi I z. And now if you remember, when we proved that the Picard group, it's isomorphic to this H1M OM star, remember that the correspondence was not that GJK goes to GJK, but the GJK goes to GJK inverse. So recall that L corresponds to GJK inverse in here. And so if you want to compute this, C1 of L, all you have to do is compute the delta of this object, where delta is the morphism. Maybe let's give a name to this guy. Let's call it sigma L. And delta is the snake lemma map. Yeah. So, okay, we have to compute this operator coming from the snake lemma. So let's write down the relevant part of the diagram. So we know the snake lemma takes something here and gives us something there. And we don't need all the rest. All the rest is needed, let's say, to prove that this is well defined. But now we know, thanks to the snake lemma, that whatever you just trace everything back and whatever you get is well defined and it's unique and et cetera, et cetera. Okay, so we start from here. Maybe I'll use a different color. We start from here with this GJK inverse. Okay. We want to go back. So what's a possible anti-image here? Well, it's simply minus 1 over 2 pi I log GJK. Because remember that here we have the exponential map. So this line here is the exponential map. Okay, remember exponential is exp of 2 pi I times the function. So if you look for an anti-image, is what you get. And it's minus because, of course, here we have a minus. Okay. Okay, so now we go down. And well, you see, well, when we go down, you get precisely this object there. Because now you have to take, alternating indices. So let's start, let's say so this is minus 1 over 2 pi I. So we can simply bring the I above and delete this minus. So I over 2 pi, which is what we have here. And then you simply have to alternate the indices. So you have GK with the plus. Then when you remove the middle one, you should get a minus. Then when you remove the last one, the first one, you get a plus again. Okay. So here you get precisely this ZJKL that we saw before. And when you get back here, this is still the same. Because this is just inclusion map. Yeah. So this proves this representation. So the first term class of a line bundle is represented by this alternating sums of logarithms in this check homology with respect to a cover, such that these intersections are simply connected. Okay. Okay, so we can play with other exact sequences. We have another exact sequence. Maybe yeah, next page is fine. We have another exact sequence, which is the one defining divisors. So we have 0, OM star into OM just inclusion. And then here we take the quotient is the exact sequence defining divisors. Defining divisors. No? And again, this gives a morphisms. It gives H0 M dm, which is nothing but, as we know, the global sections. This is the snake map. And here we have, again, the Picard group, the manifold. And if you remember, we already saw a connection between divisors and line bundles. Every time you have a divisor, you can associate a line bundle to it. No? And perhaps this is exactly what we were doing before. So let's take a divisor. And we define O of D to be simply the bundle associated to D in the Picard group. Okay. And remember that if D is a Cartier divisor, Cartier divisor. So in fact, you know, a global section of this, so an element here, there exists a cover of M and non-identically zero meromorphic functions. So that the ratio is non-zero on the intersections. And then simply this bundle associated to the divisor is represented by the class of M beta over M alpha. So this is the alpha beta position in H1 U star M. Okay, this is simply this map. And this means that the transition functions for this bundle O of D are M alpha over M beta. Because remember, again, the isomorphism between the Picard group and this cohomology group takes the inverse of the maps. Okay. So the exercise here is to verify that this construction, so this way of associating a bundle to a divisor, is the same thing that we already did. To the one we discussed when introducing divisors. Yeah, so basically what I'm saying here is that before, okay, we just take these divisors, we don't know what they are, but we notice that they give us line bundles. Great. And what I'm telling you here is that this is something a bit deeper. Yeah, it comes from the fact that the divisors are defined by this exact sequence. Okay. And then you have the snake lemma that gives you a morphism, and this morphism is precisely this association. Okay. And maybe just a small observation. Let's say that we have two distinct divisors. Yeah. And then they give the same line bundle. So giving the same line bundle means that they have the same image here, right? So they differ by something in the kernel, which is nothing but something in the image of the previous morphism. So what we need is a global meromorphic function not meromorphic, sorry, of course, holomorphic. That'd be weird. So a never zero holomorphic function on all of them, such that d minus d prime is the divisor associated to this. Sorry, 1 second. I think I'm doing something wrong. So okay, to give the same object here means you differ by an element in the kernel, an element in the kernel of the next map. I know that here
Yeah.
should be meromorphic. I'm just not sure where it's coming from.
I think it has to be just O star. And,
No, it should be M star. Because O star, like the divisor associated to M to any function, you know, star is empty. Where because we do have a morphism from meromorphic functions into divisors as well, no? Oh, let me think for a second. So if the delta is the same,
hmm?
right? So if delta of d minus d prime is 0, or the trivial bundle, yeah? Yeah, so it looks like it should be something in the image of OM, right?
Where the image, the image of the map from OM to DM.
I agree to that. I mean, it looks like there should be some function not in M star, but simply in OM, not even in OM star, right? Just in OM.
Yeah, yeah.
Yeah, that makes a lot of sense. That makes more sense. So an effective divisor. I will double check on this. But this makes a lot of sense, yes. I mean, this we know. This is for sure from here. I don't know if you can also say it for meromorphic, but I don't think it should be true. Okay. Yeah, I mean, this makes sense. You're simply saying that two divisors give the same bundle if they differ by an effective divisor. Remember, the first we introduced was effective divisors, which are basically the zero holomorphic functions. Okay. So we know what is a meromorphic function, just a ratio of holomorphic functions. But another thing we want to introduce is meromorphic sections of a bundle. So we know that when we have a bundle, particular line bundle, we know what are its holomorphic sections, but we have never defined its meromorphic section. And of course, the idea is to just say that this is locally things which are locally meromorphic. But now we have some better looking machinery to define all of this. So we take a line bundle on M, and we take L, cursive L. We take this sheaf of sections, of holomorphic sections. And now we simply say that a meromorphic section of L is an element of H0M, meromorphic on M, tensor over holomorphic on M, L. Okay. Which is kind of the same as saying things which are locally meromorphic, but it looks a bit more fancy. And in particular, it already tells us that this is some nice structures, right? Because for instance, these are both OM modules. So this is an OM module. You have the linearity and you have a few other nice properties. Okay. So let's see this thing that I was saying. So what do these objects really look like? So let's start with the line bundle over M with transition functions G alpha beta with respect to a given cover. Which is trivializing for L. Trivializing for L. So if M alphas are such that they each are meromorphic functions on the respective open sets, and they satisfy what we can think of a gluing condition. Yeah, so if M alphas and beta were holomorphic sections, then this would simply mean that they glue to a global section. What we're saying in this proposition is that the same is true for meromorphic sections. Yeah. And the vice versa is also true. If we have a global meromorphic section, then there is a trivializing cover. Trivializing cover U alpha for L with transition functions G alpha beta and M alphas local meromorphic functions which glue. Okay. So the intuition is correct. So basically what we defined meromorphic section to be just an element of this abstract sheaf. Yeah. But in practice, what this means is what we want it to mean. And that is that meromorphic sections of a bundle are basically, I express the locally by meromorphic functions, which glue according to the transition functions of the bundle. Okay. So let's prove this. Need a few more seconds. Okay, so the idea is to define some kind of basis of sections for the our bundle L. So for each alpha, we take E alpha to be a global section, which is never 0. And such that they behave in this way. So E alpha is G beta alpha times E beta. So this is something we saw when we did the, I think when we did the fine line bundles, maybe. Sorry, not the bundles. We did this for bundles in general. And the idea is that the coordinates change with G alpha beta, but the sections change with G beta alpha. Okay. So if you don't remember how this was obtained, the sections, the alphas were obtained, you can just think that actually, so E alpha is simply the anti-image of X1. And they behave well. Okay. And another thing that we observe is that M alpha tensor E alpha is of course a section here. Okay, so this is by definition, the M alpha is a section of this this sheaf, and E alpha is a section of this sheaf. So this is well defined. But the nice thing is that on U alpha intersected U beta, if this is non-empty, we have that M alpha tensor E alpha is nothing but M alpha tensor G beta alpha E beta. And now, since this tensor product is over the sheaf of holomorphic functions and G beta alpha is a holomorphic function, this becomes G beta alpha M alpha tensor E beta. But then this is simply M beta by our hypothesis, yeah? So our hypothesis that this we had this equality here. So in particular, the glue. So M alpha tensor E alpha defines a global section. Okay. So, I mean, this maybe the machinery looks a bit hard because you're taking tensor product, but there's really nothing. You're just thinking that, okay, I have a vector, this E alphas in betas, and normally I put holomorphic functions in front of it to get holomorphic sections. And now instead I put meromorphic functions in front of it. And this gives me meromorphic sections. So let's look at the other direction. This is very easy. So M is your global section, global meromorphic section. Then we do have a cover. And sections V alphas, which are in M and U alpha tensor over holomorphic functions on U alpha of L of U alpha, such that V alpha restricted to U alpha intersected U beta is the same as V beta restricted to U alpha intersected U beta. Yeah, and of course, this V alpha is nothing but M restricted to U alpha. Okay, so this is simply the definition of, I mean, we look at the local data of this section. So let us assume that this cover is trivializing. For L, which we can just shrink these open sets. And with respect to the cover, we have transition functions. G alpha beta. Yeah. And now necessarily we have, so again, the alpha must be some M alpha tensor E alpha for some M alpha in MM U alpha. And what is the reason for that? Is because this E alpha, it's a basis because it's never zero. So it's a basis of sections for L U alpha. So whatever section you have on a trivializing thing would be holomorphic function time E alpha, but then the holomorphic function part, we can always send it to the left. Okay, so it's simply meromorphic function times E alpha or some M alpha in here. And now we know two information. So we know that, of course, E alpha is G beta alpha E beta. And we know that, as we wrote before, M alpha tensor E alpha is the same as M beta tensor E beta. So now we can substitute the alpha with G beta alpha minus E beta. And in particular, this gives us then M alpha minus G alpha beta M beta tensor E alpha is 0. Yeah, substitute, then I bring to the left. But then, of course, E alpha is never 0. So what we get is that M alpha is equal to G alpha beta M beta, and we're done. Okay. So we proved the inverse implication. So what was the reason to introduce meromorphic sections of a bundle? Well, we already know that meromorphic functions overall are somehow linked to divisors. Yeah. Because holomorphic functions give you, there's 0 holomorphic functions give you effective divisors. But if you look at meromorphic functions, you take like zeros minus poles. This is all possible divisors. And the thing is that we don't need just a meromorphic function. It's enough to have a meromorphic section of some bundle to give you a divisor. So let's see this link. So we have a line bundle over M. Then there exists a divisor which represents that bundle. If and only if L admits a global meromorphic section, which is not identically 0, of course, identically 0. That's it. And furthermore, D is effective if and only if the section is holomorphic. This global meromorphic section is actually holomorphic. Okay, so here we see a bit more this relationship between line bundles, meromorphic sections, and divisors. Proof. So we have the inclusion of holomorphic non-zero functions into meromorphic non-zero functions. And this induces a mapping homology, which is not necessarily injective anymore. the map induced by the inclusion non-zero holomorphic functions, in particular non-zero meromorphic functions. And again, here we have an exact sequence, which is this one. So here we have the snake lemma map. And here we just include. And this one is exact. And why is this one exact? Why is this one exact? I know it. Did I make a mistake when I defined the divisor thing? This is not the divisor, is it? Oh my God. I'm sorry. Okay, then now this explains a lot. This is not how you define divisors. This is how you define divisors. And this is the inclusion map. Okay. Sorry about that. Okay, so here we were right.
That's actually better because now I understand that it's injective, the first map. Yeah. Oh, okay.
Yeah, sorry about that. So this was correct. This was in fact M star. And this is M star. Oh, sorry about that. It's
Okay,
terrible.
no problem.
Okay, but everything else works because fortunately we didn't use this exact sequence anymore until now. So yeah, divisors are defined as never zero meromorphic functions, modulus never zero holomorphic functions. Yeah, that would have been weird. And now this is exact because this in fact comes from the exact sequence, from the short exact sequence defining divisors. Okay. So in particular, I of L is equal to 0 if and only if there exists a divisor which maps to this L. Okay. So this is what we're trying to characterize. Yeah, we're trying to characterize what it means for L to be expressed by a divisor, to be represented by a divisor. So we see that this is equivalent to us that the image in here is 0. So what does it mean? So let's make this explicit. So if L is given by G alpha betas, we know it is represented by G alpha beta inverse in here. So now this equivalence class is not only representing the fact that we are in a cohomology, it's also representing the fact that we need to take a direct limit. Huh? Yeah. So assume now that so I'm gonna, I mean, this technically is not I, right? Because this, I'm not naming this isomorphism. That's the point. Okay, so I'm really identifying the Picard group with this H1M O star, but in reality, I should really give it the name and blah, blah, blah. But let's say if I say I on L of L, I mean this. If I say I of some transition functions, I mean this. So let's assume that this is 0. But this is equivalent. So being 0 here simply means that your what it means this is a kernel modulus image, so you're in the image. So there exists some M alphas such that the delta of this M alpha in position alpha beta, which we know is M beta divided M alpha, it's equal to G beta alpha. Okay, so this would be, because this is the same as G alpha beta inverse. Okay, so we're asking that something is zero in cohomology, means that you're in the image, right, of this delta map. And the delta map of some meromorphic section here is simply M beta divided M alpha. And we want this to be equal to this G alpha beta inverse, which is nothing but G beta alpha. So, hence D H0 M dm such that O of D is L is given precisely by this by these M alphas. And in particular, they glue to a meromorphic section of L. So why do they glue to a meromorphic section of L? Well, simply because M beta is equal to G beta alpha times M alpha, and we saw in the previous proposition that this is the same as being a global meromorphic section. Okay. So this is one direction. Vice versa. We need to show that if you do have such a meromorphic section, then you are represented by a divisors. So let's say we have this meromorphic section. Data of a meromorphic section of L. And we take the Cartier divisor, the Cartier divisor defined by these local sections. Yeah. And then if you just copy what we just did, then copy what we just did, you're done, simply because, where is it? Yeah, so you take, okay, you have these global sections, which is not identically zero, and then you take the Cartier divisor defined by these M alphas, and then you associate a bundle to it. So what are the transition functions for this bundle, where these are M alpha over M beta, right? Which is precisely then G alpha beta, because M alpha over M beta is G alpha beta. Okay. So it's like the same proof in reverse. You can think that these are all ifs and only ifs. And yeah, the extra condition, yeah, for this effective is only if the section is holomorphic. Well, we know that an effective divisor is one by representing not by meromorphic functions, but by holomorphic functions. Yeah. And in that case, we know that the divisor is effective. What is it? And vice versa, if you're effective, this M betas are holomorphic, so everything works. Again, it's the same. So basically, instead of writing here M star M, you just write holomorphic functions. Okay. As an exercise, we see that given a meromorphic section of L, then M tensor Q defines a meromorphic section of LQ times itself by using M alpha to the Q as local data. I mean, this is a very easy exercise. You just look at this equality, you put it to the Q, and you see that G alpha beta to the Q are the transition functions of LQ. So you're done. Why did I put this exercise / observation? Is because finally we're actually very close to understanding the tautological bundles. So if you remember tautological bundles over complex projective spaces, we saw them. There were Z many of them, and we saw, and in particular, they're a subgroup of the Picard group. I promised you that this is the Picard group, and we're almost there to prove it. I don't know if we'll manage today. So let's give an example. So let's take U0 to be the good old open set in CPN, where Z0 is non-zero. And we take S0 from U0 to O minus 1, which sends one of these Z's to Z, comma 1, Z1 over Z0, Zn over Z0. So this is a holomorphic section. It's of course well defined because this is homogeneous. Section of, so but this is holomorphic of course only on U0, but it extends to a meromorphic section. On the all of CPN. Yeah, you just take the same expression and you see that it glues well. So this defines a meromorphic section in CPN. And in particular, it has poles of order 1 on the hyperplane Z0 equals 0. Right? And he has no zeros and just poles there. So if you take its tensor inverse, yeah, so the one that is locally defined by the inverse, this is a holomorphic section. Of what? Of course, of O1. Yeah. And this implies that O1 is nothing but the bundle associated to this divisor. So we think of this H as a divisor. But this is something we already saw, yeah?
Yeah, could you go on? Yeah.
Oh, sorry, yeah, back here.
One slide back.
With the example, no? So, okay, so we have this section, which is only defined on U0 as a holomorphic section, but of course it can be extended to the all of CPN. And on CPN, it has poles of order 1 on this hyperplane Z0 equals 0 and nowhere else. And he has no zeros, right? Because this is just 1, for instance. So if you take the inverse meromorphic function, this is going to be holomorphic with zeros only on this hyperplane. So this is now a holomorphic section of O1, and by this proof that we saw before, this tells us that O1 is O of this divisor. Okay, and you can think that also, for instance, also O of -1, you can think in O of negative this divisor. Yeah, because this is poles only here, for instance. And this has very much to do with the fact that this H is an hyperplane, in particular as algebraic degree 1, meaning it's defined by a homogeneous polynomial of degree 1. And this is also something I hinted back when we did this. And we actually showed that every time you take a hyperplane, so the zero of some of a homogeneous polynomial of degree 1, so just of a linear function, this defines the same bundle, which is O1. We did that. And the idea was that if you take a homogeneous polynomial of degree n and you do the same game, here you should get On. But this is a bit harder to prove, but now finally we have the tools for it. And in fact, it will be just an exercise. So we take an homogeneous polynomial of degree m, greater or equal than 1. Prove that P defines an effective Cartier divisor S given by P equals 0 on CPN, and prove that the associated bundle, actually maybe before that, proof then that F defined as Z0 to the M, so like a prototype homogeneous thing of degree M, divided PZ is a global meromorphic function, so not a section but a function on CPN. So meaning really that F is M CPN star CPN. And from this, deduce that M times H, so this is in divisor notation, minus S is equal F in this world. So in the world of divisor and CPN, and hence by what we saw before, so two divisors is the same if they, sorry, they're not the same, but they define the same bundle if they differ by a by a divisor defined by a meromorphic function, is that OM, which is O of M times H, this can be referred directly, is the same as O of S. Okay, so this equality, say we know it, if this is true. Yeah, this is what we said before. If the difference of two divisors is the divisor generated by a single meromorphic function, then the associated bundles are the same. And this one, you can just think that so we know that O of H is O of 1, and then you know that the associating a divisor to its bundle is a morphism of groups, for instance. Okay, so you can think this as O H, O H plus O A, sorry, not plus, but tensor H, which of course is just this. Yeah. So this is, let's say, from the fact that everything here is a morphism of groups, of Abelian groups, and this one is from the fact that these two differ only by number, by a meromorphic function. Okay. I think this is an interesting exercise because it gives us, I mean, on CPN now we have this very much complete picture. Not really, we still don't know yet. I think this is for tomorrow. We still don't know that in fact this is the Picard group, that the Picard group is precisely all these OMs for M and Z. But at least we see that these OMs with positive M's are the zero, are simply the bundle associated to any algebraic surface of degree M. Okay. Algebraic surface of degree M just means the zero set of a homogeneous polynomial of degree M. So I think this will be it for today.